Hello, I'm Richard Bowen. In this video, I'll discuss our paper, Dimensions of Motion, Monocular Prediction through Flow Subspaces. Consider this image of a street scene and imagine that this is a frame from a paused video. How will these pixels move when we press play? Well, there's not a single answer. The person on the bike might move closer. The other people might walk slowly. The camera itself might move. Or any possible combination of these things could happen. The number of motions is infinite. If we happen to have the next frame of video, we could represent this motion as an optical flow field. This flow field represents one of the possible motions that could arise given the first frame. But our video is paused. We only have one frame. What can we say about the optical flow that could arise? Naively, the set of possible flows is huge. You could have any two vector at each pixel. But intuitively, we might think that the dimension of plausible flows, given this frame, is much lower. For instance, since the camera motion has 6 degrees of freedom, we might expect the space of flows has dimension 6, plus some small set of parameters describing how fast the cyclists and walkers are moving. Here's a visualization of what a basis for the flow subspace might look like for this image. As it's a linear space, all plausible motion should be obtainable as a linear combination of these basis flows. The key idea in our paper is to predict this subspace from a single image. However, we know that this subspace is very structured. It will depend on both the shape of the scene, in the form of a depth map, as well as things like what pixels belong to objects that can move. That's why you can see object boundaries in some of these basis flows. We show that the relationship between these flow subspaces and scene properties like depth allows us to learn these properties from video solely by using flow as supervision. In particular, we use flow to supervise monocular prediction of two things, disparity and a soft instance segmentation. Disparity, or inverse depth, is a common primitive in 3D vision. The other monocular prediction our method makes is this soft instance segmentation, with an example shown here. It's a low-dimensional embedding that maps different object instances to different parts of the embedding space. For example, the cyclist has been mapped to all yellow, and the car on the left to all teal here. A nice advantage of our method is that it learns to predict both disparity and this instance segmentation in a self-supervised way from in-the-wild videos. Unlike some other approaches to self-supervised learning of disparity, we don't need to run MVS or use camera poses. This is because we are using flow as supervision. So, here's our overall pipeline. First, the network produces a scene representation from a single instance frame, consisting of disparity and object embedding. When we're training on static scenes, we might omit the object embedding. Then we generate an optical flow basis from the scene representation. We do this analytically. There's no learning at this step. I'll go into more detail shortly about how this is done. How are we going to supervise this optical flow basis? Well, we take the same input frame that we fed to our network, plus another nearby frame from the same video. We feed them into a state-of-the-art network, RAFT, that can compute optical flow between two images. This gives us our observed flow, which is a stand-in for ground truth flow. The loss on our whole network is just how close the observed flow is to the predicted subspace. We compute this with a differentiable SVD solver. That's actually a little tricky, and there are more details in the paper. Everything including this projection is differentiable, so we get gradient back into the scene representation. Just to be clear, the flow network is frozen. We're not fine-tuning it with these gradients. So that's all we need to train our system. Pairs of images from videos and the pre-existing RAFT network. Let's contrast that to a few traditional ways of self-supervised disparity learning. Some methods use a multi-view stereo step to produce a pseudo-ground truth depth in the form of, for example, sparse point clouds. This is an expensive and time-consuming pre-processing step. Some methods use photometric loss. They warp the input image based on predicted disparity, then see how well the second frame is reconstructed. To warp, you need to know relative pose, either pre-computed or computed at train time with a separate pose network. Using our flow projection loss avoids the need for multi-view stereo preprocessing, a separate pose network, or ground truth camera poses. Now I'll walk through the details of how we produce these bases from the scene representation. Let's start with a case where we are just predicting disparity. In this case, We are assuming that the scene is rigid and has no moving objects, so all the flow is from camera motion. We should expect to get a six-dimensional subspace, corresponding to the 6 degrees of freedom of the camera motion. What happens if we move the camera a small distance in x, y, or z? The flow depends on the disparity, as shown here. Rotation about any of the 3 axes produces flow fields like this. They don't depend on the scene at all. The x and y rotation flow fields, as you can see, are slightly curved, and this curvature depends on focal length. But a common situation within the wild imagery is that we don't know camera intrinsics at training time, so we use a trick. We replace each of these by a pair of fields. So, from disparity, we can produce this 8-dimensional basis for flow. Here are some results on static scenes. We trained on Real Estate 10K, a YouTube dataset of in-the-wild videos of real estate tours. Here are some example results on test scenes. The second column is the predicted disparity, and the last 3 columns show how well the RAF flow was projected into the predicted subspace. As you can see, our network, by trying to minimize the flow error, has learned pretty reasonable disparity prediction from single images. Since the flow itself is smooth and has well-defined edges, we find that we don't need to add any explicit edge-aware smoothness priors. Real Estate 10K doesn't feature ground truth depth maps, so, following previous work, we train on RE10K and test on IBMS and NYU, 2 common test datasets consisting of indoor scenes with depth from a laser scanner or a depth camera. What we find is that quantitatively, the depth maps we get are comparable to state-of-the-art on this setup, without the need for expensive preprocessing or separate pose network. What about scenes in which not only the camera but also objects might move? How will we generate an optical flow basis here? As before, from a single image, our network predicts the disparity at each pixel, and now it also predicts an object embedding. At each pixel, that's a unit vector in a 6-dimensional embedding space. We already know how to generate the flow corresponding to camera translation in x, y, and z from the disparity. And the flow from the camera moving in a given direction is identical to the flow from the world moving in the opposite direction. We will use this observation to generate a basis for object translation. We take each dimension of our object embedding space separately and multiply it pointwise by the 3 global translation flows we obtain from disparity. In the resulting basis, pixels with different vectors in the embedding space move independently in x, y, and z. As long as the network maps objects that might move to points in the embedding space that are linearly independent, then this basis accounts for the potential flows from each of them translating independently in arbitrary directions. So our overall basis for dynamic scenes is this basis for object translation, derived from disparity and the object embedding, together with the camera rotation flow basis, which is the same as in the static scene case. For the dynamic case, we also mined a dataset from YouTube, which we call the Walking Tours dataset. This dataset consists of videos taken by people walking around large cities. Here are a few examples. The object instance embedding from the network is shown using PCA. As you can see, the network has learned to separate instances, even of the same semantic class. It also oversegments some, putting embedding space edges at large depth boundaries. To explore the instance embedding a little more, we performed a simple proof-of-concept segmentation experiment. We hand-labeled a single seed point in each of a few objects and the background. Then, each pixel is assigned to one of the seeds according to a simple bilateral heuristic. To reiterate, this is a soft instance segmentation learned in a self-supervised way. There are a few limitations we want to discuss. First of all, we are limited by flow quality. Modern flow networks are pretty good and transfer across datasets well, but sometimes the off-the-shelf network we used does get the flow wrong in large textureless regions. Here, the tree has confused the network into assigning the wrong flow to a large part of the sky, for example. On datasets where objects tend to have motion that is very strongly correlated with the camera, there's a failure mode, which puts such objects at very wrong depths. Correlation like this is common in self-driving car datasets like Kitty. When trained on Kitty, our model sometimes, but not always, puts cars that are moving parallel to the camera at very large depths, as shown in the lower right example. A natural question is whether, given the subspace, we could sample a flow to produce a realistic-looking animation. But because there isn't a sense of a distribution over flows, random sampling from the subspace gives animations like these. While individual objects move together, they don't move in realistic ways, hence the cars floating off the pavement. And there's not a way to distinguish object from camera motion. That said, Since the dimension of the subspace is generally pretty small, there is a natural way to use projection to get a flow that's been constrained by user input. Here I picked these 6 points and chose a motion direction for each one, and just by solving some linear equations, I can get a nice, full scene flow. This is a future direction. For more information, to read the paper, or to reach the authors, please check out the project website. Thank you for watching.